Earth is fantastically beautiful. On this channel, we have mainly focused on planets in our solar system, and have seen spectacular flyovers of the Moon and Mars. But our endeavour to discover and understand new worlds may have meant that we have neglected what is probably the most beautiful planet that we know of. Our home. And after some of the views I'm about to show you, I'm a little worried that you may never want to look at another planet again. I'm Alex McColgan, and you're watching Astrum. And in this first episode, we will look at some of the most spectacular mountains in the Middle East, with real time lapses seen from the perspective of the International Space Station. And I will explain the context to these images to give you a true appreciation for what it is you are looking at. Let's start with an impressive look at some of the mountain ranges either side of the Red Sea. We are orbiting Earth at an altitude of roughly 350 kilometers, currently heading in a southwardly direction with Egypt to our left and Saudi Arabia to our right. It may seem like we are only looking at a small area, but in reality this view is 400 kilometers across. The mountains to our right are the Sarawat Mountains, a large range that covers over 180,000 square kilometers and rises well above 3,000 meters. You'll notice riverbeds running down the mountains. Although these riverbeds are dry in this video, this range sees the most rain in the whole Arabian Peninsula. They just tend to get it all in one go. Have a look at this enormous crater here. This is not an impact crater, but rather the remnants of a volcanic crater. This whole region is actually formed from volcanic activity, with some volcanoes still being active today. These white dots here are not a city, but rather a huge cement factory. Just under these clouds is the famous city of Mecca. And just overlooking it are some fantastic mountains and winding roads. As you can see, this area is extremely arid, although in other parts of the mountains, vegetation can be found. Let's speed up our journey a bit now, heading towards the tip of the peninsula. On the far right is the edge of the Arabian Desert with its famous Sif, or longitudinal dunes. These dunes stretch for hundreds of kilometers around the Arabian Peninsula, following the direction of the wind, which is a constant in this area. Seen just at the border of the desert and the mountains, seems to be a scar in the landscape. This is not a valley as it may appear, but a raised ridge, with a sand dune following along the side of it. You can just about see a dam with its reservoir by here, and to the east of the dam, in the middle of the sand, is a farming town. The harsh environments humans can grow crops astounds me. Also found in this region is Jabal an-Nabi Shuaib, the tallest mountain on the Arabian Peninsula, reaching 3,700 meters tall. Let's start heading west from here now. Underneath us is the east side of the Arabian Desert, individual Sif dunes just about visible from this angle. The Euphrates and the Tigris rivers are flowing from the north towards the Persian Gulf in the south. You can see how these rivers visibly nourish the ground of Iraq, with most of Iraq's towns and settlements found within this region. This is known as an alluvial plain, a flat region of land where these rivers have flooded over time, creating fertile soil. Beyond Iraq and to the left, you see the mountain range running through Georgia and Azerbaijan, separating Europe and Asia, called the Caucasus Mountains. These mountains are the result of a tectonic plate collision between the Arabian plate moving northwards into the Iranian plate, folding the ground upwards into the peaks you see today under the pressure. Found in this range is the highest peak in Europe, Mount Elbrus, which reaches 5,642 meters tall. Unlike most of what we've seen today, this area is lush in vegetation, and the mountains feed hundreds of glaciers into the valleys below. In stark contrast to these green mountains all in a line, in Iran, to our right, we have an almost surreal-looking set of mountains. Surreal because the peaks are poking out of the cloud cover or fog. These are all part of the same range, called the Zagros Mountains. As you can see, they are vast, spanning 1,600 kilometers in length. Let's have a closer look at what makes these mountains so interesting. These mountains were also formed due to plate tectonics, although in a different process to the Caucasus Mountains we looked at earlier. One big visible difference you'll notice is that the vast region has linear mountains, but not just in a single row, but rather it has many peaks and troughs like corrugated iron. The fault that these mountains formed on is called a fold and thrust belt, through collisions with the Arabian plate moving into the Iranian plate. But let's zoom out to the wide-angled view again. If this is all the Zagros Mountains, then why do these mountains in the south look so different to the ones in the north? This is due to it being comprised of different types of rock. In the south, sedimentary layers are deforming over a rock salt layer, meaning folding happens a lot easier in this type of rock, whereas to the north, the rock salt layer is either very thin or missing altogether. The rock layer that does exist here is not as ductile or plastic as the rock salt, meaning the landscape is only deformed along a much narrower band along the fault line. Interestingly, it is around the parts of the exposed rock salt layer that most of Iran's oil reserve is found, as the salt structures are impermeable, meaning vast pockets of oil can be retained. Salt domes and glaciers can be exposed to the surface, and I must say they form some of the most bizarre landscapes I've ever seen of Earth. They are visible from space. Here is a giant dome 14 kilometers across. And here are some salt glaciers. Yes, these structures flow down into the valley in a similar fashion to a water ice glacier on Earth. A close-up inspection of the salt shows layering and erosion from the rain. And looking out over the landscape shows an otherworldly view. The Zagros Mountains to the north are a lot more normal looking, but that's not to say they aren't beautiful in their own right. Beyond the Zagros Mountains, but just before the coast of the Caspian Sea, we can see a lake called Lake Urmia. This lake used to be the largest lake in the Middle East and the 6th largest saltwater lake in the world, with a surface area of 5,200 square kilometers. However, since the 1980s it has shrunk to only 10% of its former size, as dams have stopped the flow of rivers into the lake. If the lake ever dries up completely, this could adversely affect the climate in the area, and plans are in motion to refill it. Next to the lake though is an old volcano, which is easily visible against the lighter coloured ground around it. But zooming out a bit, we see that this volcano is tiny in comparison to this mammoth, known as Sarhan, at 3,707 meters tall. This means that even though it is found in the Middle East, it's tall enough for there to be a ski resort on it during the winter. Heading further east, we come to another range of mountains bordering the Caspian Sea, called the Alborz Mountains. As you can see, Iran is actually a very mountainous country, and although we have such a wide field of view from this shot, the largest mountain in Iran, Damavand, is easily visible. Just south of it is the capital of Iran, Tehran. But let's have a closer look at Damavand. This impressive volcano is the tallest in Asia, at 5,609 meters. And it is still active, although it hasn't seen an eruption in an estimated 8,000 years. Although it hasn't erupted for so long, it's considered active because it emits sulfur regularly. It even has a volcanic crater at the top. And what's really impressive about this volcano is how high it rises in comparison to anything around it. The Alborz Mountains make an impressive sight for those living in Tehran too, rising high above the city with snow-capped peaks. Moving beyond Iran, we start to leave the Middle East, and also the scope of this video. Earth, of course, has storms. Some to us appear massive and can cause millions of dollars worth of damage. In the grand scheme of things though, they're not that big. Compared to the biggest storms we know about, that of the Great Red Spot on Jupiter, they're pretty tiny. But for us mere mortals, we need to understand these storms in order to protect people and property as best we can. Right now we're going to look at a notorious hotspot for cyclones, the Bay of Bengal near India, and at a cyclone, Philin, that ran its course from the 8th to the 14th of October in 2013. The cyclone started off as a depression, but very rapidly intensified over the course of 2 days. By the 10th of October, it had properly become a very severe cyclonic storm, equal to a Category 1 hurricane. The next day it became Category 5, and the second strongest system to ever make landfall in India. But because of frictional forces over land, by the 12th it started to weaken. And by the 13th and 14th shows it returning again to an area of low pressure. If we zoom out a bit, I find it very interesting that while this is all going on, there seem to be other cyclonic systems going on over the Pacific. This typhoon season was one of the most active and most destructive for many years, as you can see by the amount of what's happening over such a short period of time. The first typhoon you see is the Category 3 typhoon Nari, or Santi. It began over the Philippines and made its way over to Vietnam before fizzling out. The next typhoon you see is Typhoon Whippa, or Tino. It got as strong as a Category 4 hurricane.
Earth is a beautiful planet, and to me visually, it's my favorite. You might also be wondering what the difference is between typhoons, cyclones, and hurricanes, and also how they are formed. The short version is that tropical cyclones in the West Pacific are called typhoons, those in the Indian Ocean are cyclones, and those in the Atlantic and East Pacific Ocean are called hurricanes. It's the longitude that makes the difference. When in the northern hemisphere, they will both spin anti- or counterclockwise, and in the southern hemisphere they will spin clockwise. And how do they form? Well, tropical cyclones are like giant engines that use warm, moist air as fuel. That's why they only form over warm ocean waters near the equator. The warm, moist air over the ocean rises upwards near the surface. Because this air moves up and away from the surface, there's less air left near the surface, and then air from surrounding areas with higher air pressure pushes into the low pressure area, and that new air becomes warm and moist and rises too. As the warm, moist air rises and cools off, the water in the air forms clouds. The whole system of clouds and wind spins and grows, fed by the ocean's heat and water evaporated from the surface. And because the Pacific is so warm, it's the ocean that will see the most tropical cyclones.
Above our planet's poles, an invisible force is at work. Hypothesized decades before we were able to measure it directly, this global energy force is responsible for sculpting our atmosphere and driving charged particles into space. It's also why some planets end up uninhabitable altogether. It's called the ambipolar field, and it's a force as fundamental to our Earth as gravity or magnetic fields. Although, for the sake of life on Earth, it's a good thing it isn't too strong. Recent breakthroughs from NASA's Endurance mission have finally allowed scientists to solve a 60-year-old mystery by measuring the ambipolar field for the first time, proving once and for all that our planet has a third global energy field. I'm Alex McColgan, and you're watching Astrum. Join me today as we unravel the mystery of our planet's ambipolar electric field, a phenomenon that not only powers the polar wind, but also has an enormous impact on our planet's habitability. Earth's magnetic field, depicted in this video as onion-like layers of lines, helps to shield our atmosphere from dangerous solar energy and damaging cosmic rays. And the gravitational field, shown here as the white glow around our planet, not only keeps us planted on Earth's surface and stops our atmosphere from drifting away, but also provides valuable information in the study of Earth's changing climate, sea level rise, ocean circulation, and much more. As you can see, our magnetic and gravity fields are critical features that help make our planet habitable. And with the recent publication of a 2024 paper in the journal Nature, direct evidence has been found for a third energy field, the ambipolar field. To understand this energy field, we need to talk about plasma. Like a solid, liquid, or gas, plasma is another state of matter, which happens to make up 99% of all visible matter in the universe. Plasma is made of ionized particles and is responsible for several well-known phenomena on Earth like the aurora borealis and lightning. Plasma can form where atmospheric gas density becomes low enough to support the conditions for it, and around 90 kilometers above Earth's surface. This plasma is made up of very lightweight, fast-moving particles, which get trapped along the Earth's magnetic field lines as they move away from the surface. Around the majority of our planet, plasma encounters a barrier that limits its escape into space, known as the plasma pores. Here, plasma co-rotates along with Earth along its closed magnetic field lines. Until the mid-1960s, the prevailing model of our planet's magnetic field theorized that all of the magnetic field lines were closed and the plasma remained trapped. So, what changed? We went to space. In the 1960s, the first spacecraft flying over our planet's north and south poles could actually detect a supersonic wind of charged particles, or plasma, flowing out to space, including positively charged hydrogen and oxygen ions. This observation led scientists to start wondering whether the Earth's magnetic field model should have an open rather than a closed tail. At the time, scientists already knew that our atmosphere lost some particles to space due to thermal escape. This is a type of atmospheric escape that typically happens when the energy from sunlight heats up particles in our atmosphere, allowing them to reach escape velocity and break free of our planet's gravitational pull, kind of like when a pot of water boils and steam evaporates. So it was no surprise that some particles would be escaping into space, but something didn't quite add up. If energy from the sun were the only cause of atmospheric escape, one would expect the particles that were escaping into space to be heated. However, many in the stream were actually cold, with no signs of being heated, and yet they were traveling at supersonic speeds. Scientists hypothesized that there must be another invisible force driving this phenomenon, and in 1968, the term polar wind was coined to describe it, leading to more research and theories into its cause and effects. The idea of a planet-wide electric field was developed to explain the polar wind. But when this was theorized in the 1960s, it was thought that the force was too weak to detect. And at the time, scientists were correct. The electric potential was so weak, it would require very sensitive instruments to measure, and that technology wouldn't be invented for several more decades. Enthusiasm to measure our planet's ambipolar field was spurred again in 2016 after a clue came from the European Space Agency's Venus Express mission. One of the reasons that Earth is hospitable for life is because of its water, while Venus today is dry and barren. However, billions of years ago, evidence suggests that Venus might have had abundant water like our own world does now. This raises the intriguing question: if Venus once had water, where did it all go? The ESA's Venus Express mission offered a potential explanation when it detected a 10-volt electric potential around Venus, at least 5 times larger than expected. This marked the first successful measurement of an electric field on any planet, including Earth. The electric field surrounding Venus could pull positively charged ions like oxygen out of the atmosphere, draining it of the essential ingredients of water, like a vacuum cleaner siphoning particles out to space. Over time, this could have played a role in draining the planet of its once abundant water. This prompted a question much closer to home. Does Earth have a similar electric field? And if so, why has our planet managed to hold onto its water? The electric potential measured around Venus was around 10 volts. For comparison, a standard car battery is 12 volts, but scientists expected our planet's electric potential to be as little as 0.3 volts, similar to a button battery you might find in a watch, and some 25 times weaker than the electric potential on Venus. It's this difference that may be a key reason why our Earth has been able to keep its water, and that's what inspired NASA's endurance team to develop a new type of scientific instrument called a photoelectron spectrometer to find Earth's weak electric field. The instrument is designed to measure the speed of electrons escaping from Earth's atmosphere as a way to reveal our planet's electric potential. Earlier, I explained thermal escape, and I mentioned that particles are able to escape from our atmosphere when they reach escape velocity. That escape velocity is a very specific, predictable speed, but this speed should be ever so slightly slowed by Earth's electric potential. And so, by measuring that slowing effect at apogee, or the furthest point in Endurance's orbit from Earth, the instrument would be able to measure the strength of the electric potential around our planet. Such a sensitive instrument would need to be launched at precisely the right location and time in order to ensure a chance at making the observation successful. The Svalbard rocket range was selected for the job,
It's the northernmost range in the world, located in Svalbard, Norway, a group of islands in the Arctic Ocean. Here, the NASA Endurance team would be able to launch the instrument on a suborbital rocket through Earth's magnetic North Pole. And on the 11th of May 2022, the team of international scientists did just that. Named after the ship that carried Ernest Shackleton's crew in their 1914 attempt to reach the South Pole and cross Antarctica, the Endurance mission launched its suborbital rocket to an altitude of 768 kilometers, collecting data over 518 of those kilometers before splashing down 19 minutes later in the Greenland Sea. During its flight, the instrument measured a change of 0.55 volts in electric potential between 250 kilometers and 768 kilometers. Space scientist Glenn Collinson, the principal investigator for NASA's Endurance mission, said even though half a volt is almost nothing, again almost about the strength of a watch battery, it's just the right amount to explain Earth's polar wind. This first ever direct measurement of Earth's electric field marked a pivotal moment in our understanding of this fundamental planet-wide energy force. The ambipolar field exists in what's called the ionosphere, a region that stretches across 3 out of 5 of our atmospheric layers. Our atmosphere is divided into 5 main layers. The troposphere, also known as the lower atmosphere, only reaches about 20 kilometers above Earth's surface and is where the majority of weather occurs. Next is the stratosphere, which extends up to about 50 kilometers and contains most of our planet's ozone that protects us from ultraviolet radiation from the sun. This layer has very little circulation and is where commercial airlines usually fly. Above the stratosphere is the mesosphere, extending up to about 85 kilometers. This is where meteors burn up near the bottom of the mesosphere layer are thick enough to slow them down. It's within the upper reaches of the mesosphere that the ionosphere begins, but its influence stretches far beyond that. Starting around 80 kilometers above the surface in the mesosphere, the ionosphere continues outward through the entire thermosphere layer from about 85 to 600 kilometers. This is where auroras happen, and high-energy ultraviolet and X-ray radiation are absorbed, creating charged particles. And finally, the ionosphere ends in the lower exosphere, which begins around 600 kilometers and continues out to about 10,000 kilometers from Earth's surface, where it fades into outer space. The exosphere is where many satellites orbit around our planet. As you can see, the ionosphere starts around 80 kilometers above sea level and stretches hundreds of kilometers into space, where it overlaps with Earth's magnetosphere, a region of space surrounding Earth. Within this massive region of the ionosphere is where we find the ambipolar field, which is theorized to begin at around 250 kilometers. While most of our atmosphere is composed of nitrogen, the upper region of our ionosphere is home to lighter elements like oxygen, hydrogen, and helium. When photons from the sun collide with these elements in the upper atmosphere, they can knock electrons loose from the elements in a process called ionization, leaving positively charged particles called ions and negatively charged electrons. Because of the opposite charges of the negative electrons and positive ions, they are attracted to each other and become tethered together by an electric field. It's this electric field that constitutes a major part of the ambipolar field. The electrons within the electric field are so light that the slightest push could send them flying out to space, while the ions are more than 1,800 times heavier than the electrons and sink toward the ground due to gravity. The subatomic tug of war works in both directions, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. This outward pressure of ionospheric electrons is what creates the ambipolar field, depicted here as the sparkling blue glow around our planet. The upward lift inflates our planet's ionosphere and accelerates some ions enough to escape from the atmosphere, creating the polar wind along our pole's magnetic field lines. What's more, the ambipolar field can achieve this acceleration of plasmas without heating them, providing an explanation for the cold plasma scientists had detected escaping from the ionosphere. It's the bidirectional nature of the interaction between ions and electrons that gives the ambipolar field its name. The Latin prefix ambi means both, and polar refers to the polar regions, where the electric field's effects are felt the strongest. Collinson, the Endurance mission's primary investigator, called the ambipolar field an agent of chaos, stripping particles from our atmosphere away into space. Hydrogen ions make up the majority of the polar wind. They are so light, the ambipolar field's upward force of these electron ions is 10.6 times stronger than the force of gravity, leading the ions to accelerate up at supersonic speeds and escape from our atmosphere above the Earth's magnetic poles. Scientists have found that our planet loses about 3 kilograms of hydrogen gas every second, or 95,000 tons per year. Additionally, the Earth also loses about 50 grams of helium per second, or 1,600 tons of helium gas per year. A smaller but still measurable amount, and a much smaller amount of other gases like oxygen. However, not all of this is due to polar winds. It occurs through a combination of factors, including thermal escape and non-thermal escape mechanisms such as polar wind. But don't worry. Despite our planet losing several thousand tons of its atmosphere to space every day, we are nowhere near running out of air. The planet won't run out of oxygen for 1 billion years. It will be another 1 billion years after that before our oceans will have been depleted of most of their hydrogen. Around 4 billion years from now, our planet may look very similar to how Venus looks now. All of our water will have evaporated, and the greenhouse effect will have become strong enough to melt rock, leaving our planet a dry, lifeless world. Keep in mind that modern humans have only existed on this planet for around 300,000 years. Our species would need to exist more than 3,300 times that length to be around in 1 billion years. While not really important on human timescales, it is still interesting to think about though. And while hydrogen ions may be the lightest and most common type of ion to escape in a polar wind, heavier particles also get a boost from the ambipolar electric field, helping to shape our atmosphere's structure and dynamics. How exactly? Well, now that we've measured the ambipolar field, scientists can delve into all the ways the ambipolar field shapes our atmosphere. Take oxygen ions for example. These heavy ions weigh half as much when they're immersed in the 0.55 volt ambipolar field. This effect increases the ionosphere's scale height by 271%, which means our atmosphere can remain denser at greater heights than it would otherwise be able to. Endurance's discovery and measurement of the ambipolar field also provided an important key to understanding why Earth has been able to hold on to much of its water up until this point, while our neighbouring planet Venus was not able to do the same. It's theorized that any planet with an atmosphere may also have an electric field, and you may recall that earlier I said Venus's electric potential was measured to be around 10 volts, roughly 18 times stronger than the ambipolar field on our own planet. While Earth does lose a constant flow of particles to space, both through the polar wind as well as other types of atmospheric escape, this effect would have likely been much more pronounced on Venus because of its stronger electric potential, leading to the loss of heavier particles like the ones that make up water. The fact that our ambipolar field is so weak may be an important part of why our planet has been able to hold onto its water. We've only just started to explore the depths of how the ambipolar field has influenced our planet and life on Earth, and the Endurance scientists have said there are already plans for additional measurements of our planet's ambipolar field in the future. Like its predecessor, the new rocket will also carry the legacy of a long-past Arctic explorer, named after the Resolute, a ship that set off to explore the Arctic in 1850. And now that we've finally been able to confirm and measure the ambipolar field strength, and with a follow-up mission already planned to take more measurements, scientists can start asking some of the bigger and more exciting questions. Like, what it means for Earth's complex atmospheric dynamics, and how it helps to govern planetary evolution. And doesn't the potential insights we stand to gain from this research feel electric? In 1977, two pioneers embarked on what might be one of the most epic feats of exploration ever undertaken. Their goal? To unravel the cosmic mysteries surrounding the solar system and our place in it. Not only did they provide us with some of the first and best imagery of our solar system's outer planets, but they continued to send us incredible new information about our universe from interstellar space, some 47 years and 24 billion kilometers later. The Voyager 1 and 2 probes are more than just instruments and circuitry. They are a symbol of humanity at its best. Curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons. It captured the hearts and minds of generations back home on Earth. When I look back, I realize how little we actually knew about the solar system before Voyager, says Voyager mission project scientist Edward Stone. We discovered things we didn't know were there to be discovered, time after time. I'm Alex McColgan, and you're watching Astrum. Join me today as we trace Voyager's iconic journey in pictures, from the splendor of Jupiter to Saturn's icy rings, to the topsy-turvy world of Uranus, to the mighty storms of Neptune. We explore what this mission taught us about our planetary neighborhood. On the 20th of August 1977, NASA launched the Voyager 2 space probe from Cape Canaveral, Florida. Its partner in crime, Voyager 1, was launched 2 weeks later on the 5th of September. Even though both probes were Jupiter-bound, Voyager 1 was set on a shorter, faster trajectory, so taking off second made sense. It overtook Voyager 2 on the 15th of December 1977 and exited the asteroid belt first. Together, this dynamic duo was set to take advantage of a once-in-176-year planetary alignment. Jupiter, Saturn, Uranus, and Neptune were going to be aligned in a way that would allow one mission to explore all four gas giants, an opportunity NASA simply refused to miss. After some back and forth with the US Congress, a few hurdles surrounding budget approvals, and a decade of hard work, the Voyager probes finally made it to the launch pad, heralding a new era of space exploration. The dazzling parade of pictures Voyager would send back were absolutely revolutionary at the time. But don't take my word for it. Let's jump in and you'll see for yourself. 13 days after launch, Voyager 1 sent this photo back to Earth. The first of tens of thousands it would send back over the next 5 years. Taken 11.6 million kilometers from Earth, it's a sentimental place to start our journey. It might remind you of the Earthrise photo taken by the Apollo 11 crew from the moon just 8 years prior. We can see our blue marble and its moon in the distance. I don't know about you, but I find this photo so hauntingly beautiful, especially knowing how far this probe had traveled and how much it's seen since then.
NASA's Mars Reconnaissance Orbiter has been imaging the surface of Mars for over 10 years now, with its powerful high-rise camera. 10 years of taking photos every day means that its catalogue is huge, and we can pick out pretty much any part of Mars that we want to have a closer look at. Today, I thought it would be really interesting to investigate the sand dunes on Mars and see how they compare to the wonderful sand dunes we have on Earth. You may have already seen imagery of the Sahara Desert, with dunes hundreds of meters tall, or the Namib Desert with rolling sand dunes as far as the eye can see. Did you know though that there are 5 different types of sand dunes, and that Mars has a type of dune Earth doesn't have? And also, what are the biggest dunes on Mars? The most common type of sand dune on Earth is the crescent or the Barkhan sand dune. While not always as distinctive as these dunes in this image, they are plentiful and found in most sand deserts. They are defined by this kind of crescent shape with arms, and they are usually wider than they are long, like you can see here. They form like this because in these places there is only one dominant wind direction. They have a shallow slope on one side that faces the wind and a slip face on the other side. They are a type of transverse dune, as they move gradually over time as the wind blows, whipping sand from the front, over the top and down the slip face. When many of them merge, they can create an almost wave of sand, smooth on the side facing the wind, with a slip face away from the wind, moving gradually over time with the wind's direction. They are also in plentiful supply on Mars. All of the ones I'm about to show you can be found at the base of various large craters. Going to this old crater near Mars's equator, Barkhan dunes can be seen lumped together somewhat here in this plane. This happens when there is a plentiful amount of sand and the dunes merge together into a big lumpy transverse dune. But individual dunes are really evident a bit higher up, where the sand is contrasted against the bedrock. Here are some more found in Arkhangelski crater. When there is a smaller amount of sand, the dunes tend to stay separate, which looks really peculiar from above. These dunes do move, although very slowly. Here's a couple of examples of dunes on Mars, moving slowly over the course of 2 to 3 years. Scientists originally thought that sand dunes would stay pretty motionless on Mars, as sand dunes require wind to move them, and Mars only has about 1% of the atmospheric pressure at the surface compared to Earth, whose winds can easily move sand. We knew the wind on Mars could pick up tiny dust particles, but it would require extremely strong winds to move sand. This could be helped though by the fact that sand on Mars is not exactly the same as Earth sand. In my Opportunity video, I mentioned that the sand particles Opportunity analysed were far smaller than what we're used to on Earth, which may aid the movement of these dunes. But what happens if the wind is bidirectional? Going back to Earth, a beautiful type of dune which can easily be seen all the way from the International Space Station is the longitudinal or Sif dune. Sif is the Arabic word for sword, which describes these dunes nicely as they are long and narrow. These linear dunes can be hundreds of kilometers long and are often found in parallel sets, separated by gravel or rocky corridors. These occur where wind directions can flip over, meaning that these ridges have a slip face on either side of the dune, making them appear quite sharp. Sif dunes also appear on Mars, and in my opinion, the most beautiful example of it can be found here. Again found at the bottom of a crater, these dunes look remarkably similar to each other, including this dusty band found on each one. Although we're not totally sure how they form, one leading theory is that they are the result of wind directions changing around Barkhan dunes. In this image, some Barkhan dunes seem to be mid-process of forming into Sif dunes. It's a really pretty image that seemingly tells a story. To our right here, we have a mesa being eroded, feeding sand into the valley below. Then you have these beautiful examples of Barkhan dunes, which show the step-by-step process of becoming Sif dunes. Another spectacular example of this, a bit further into the process, can be found here. The contrasts of the different materials in the image are stunning. And the dark sections are the sand dunes merging together. The third type of dune is the dome dune. Typically, these are not very big on Earth, usually only a few feet high. They have no slip face, they are smooth all over, hence the name. They are quite rare, and usually found in and around other types of dunes. And yes, these are also found on Mars. Here's a field full of domes, a few of which can be seen starting to cross over into Barkhan dunes. And in this impressive expanse of dunes, and I really do mean an expanse as these dunes continue on way beyond this image, you have wobbly lines of dunes with domes on the end of them. These domes seem to be much bigger here than they are on Earth. The domes here tens of meters across. This field is indicative of a change in wind direction, as the lines are nowhere near as straight as in some of these previous images. The fourth type of dune is a parabolic dune, which is the opposite of a Barkhan dune, meaning the slip face is on the other side compared to a Barkhan dune. These occur near coastal regions and form the way they do because something, often vegetation, anchors the arms of the dune in place. Lack of vegetation on Mars means it's a bit tricky to find parabolic dunes. The closest thing I found is this beautiful image, a dune wrapped around a large mound in the middle. The dune is clearly moving from left to right in this image, and you can even see the shadow of the slip face just by here on this side. The existence of this dune is heavily influenced by the size and shape of this mound, funneling wind along its walls. The fifth and last type of dune is the biggest type, the star dune. This is a dune where wind direction changes frequently, meaning the dunes in this region have 3 or more arms and are often stationary, just building up over time. This impressive image is the Sahara Desert as seen from the ISS, and it is full of star dunes. The scale of these dunes truly is impressive. Zooming in, you'll realize that these dots are people. And of course we have star dunes on Mars. Some are small, a collection of dunes merged together, but others are massive, like these found in Russell Crater, which reach far beyond this image. As this image is found nearer the poles, carbon dioxide ice can form on these dunes. During the Martian spring, the carbon dioxide sublimates, which dislodges loose material, leaving these streaks. Moving to another image, again near Mars's pole, we find one of the most beautiful images of Mars I have ever seen. This image was taken just as the sun was either rising or setting, meaning a lot of the image is shadows cast by dunes. I love this as it provides a sense of depth to the image. These again are big star dunes, with their individual arms reaching out for kilometers. There's one last thing I want to talk about the dunes of Mars. Have you ever been to the beach and seen sand ripples like these? These are actually a type of transverse dune, forming perpendicular to the direction of the water waves as they flow over the sand. Much like larger scale transverse dunes caused by the wind. Mars has these ripples too, but they are much, much bigger than what you would find on Earth, with a meter or 2 between the ripples. This size makes it difficult to see from space, but luckily we have another rover on hand, Curiosity, seen here in this image, to take this remarkable photo of them. Scientists didn't even know this type of dune existed, and it is a fitting reminder that although Mars may appear quite familiar to us, it is still a world full of secrets and unexplored facts, and there is still so much we can learn from it. Space is a desolate void, a vacuum where no sound can travel, so you might think that space is extremely quiet. You would be right, but only because you don't have the capability to hear anything with your natural ears. Turn your ears into radio wave receivers, and suddenly space is a constant symphony of strange and interesting sounds. I'm Alex McColgan, and you're watching Astrum. and together we will find out what the sources of these radio waves are and what they sound like. We don't have to go too high above Earth to already be in space. Only 160 kilometers up, and sound can't be heard anymore because there aren't enough particles for sound waves to travel. But even here in space, there are plenty of other waves to be found. The ones particularly interesting to us are electromagnetic waves, which don't require other particles to travel like sound, but rather travel by themselves through photons. You are witnessing a form of electromagnetic radiation right now in the form of visible light by watching this video. However, visible light is just a tiny section of the total spectrum of electromagnetic radiation. It stretches from waves with extremely high frequencies to radio waves, which have waves sometimes kilometers long. There are observatories that look at all these different wavelengths, and this channel has focused normally on frequencies higher than infrared, as they can easily be converted and visualized in visible light. But there are also radio observatories, some orbiting Earth right now. And we're going to check out what they have picked up in the way you are most used to witnessing radio waves at audio frequencies converted to sound. Being in Earth's Van Allen belt, or its large band of radiation surrounding the planet, and you'll already start to hear some very interesting sounds. These sounds are generated by energetic particles in Earth's plasmasphere, which are being tugged to and fro by the rotation of Earth's magnetic field. You see, there is a plasmasphere around Earth, containing clumps of ions and electrons. As Earth and its magnetosphere rotate, the magnetic fields push through these particles, accelerating them in a wave called a plasma wave, similar in a way to how disturbances in Earth's oceans can cause waves to form. You are hearing these disturbances in the form of radio waves as they pass by one of NASA's Van Allen probes. These are called chorus waves and are often heard during Earth's dawn, which is why they are found on this side of the planet. An amazing type of chorus wave closer to Earth is the Whistler mode plasma wave, which sounds like space battles and laser fire. These exist in the cold and denser part of the plasmasphere and are caused by electromagnetic radiation released by lightning striking in the atmosphere. These waves generated by these strikes can bounce around within the magnetic field of the Earth. And because higher frequencies travel faster than lower frequencies, that's why these chorus waves sound like they have a fall in pitch, like a whistle. Going further out from the plasmasphere, an opposite effect can be heard. This time, there is a rising tone, almost like a conversation between songbirds. It is thought to be caused by electrons moving towards the night side of the Earth because of magnetic reconnection in Earth's magnetotail, transferring their energy to the plasma as they collide with it. as can be seen in this simulation. In another region within the plasmasphere, we can find something called hiss waves. These are thought to be chorus waves which have leaked out from the inner plasmasphere. It sounds much more menacing and cold than the other sounds we've heard so far. I find these clips very interesting, as it's sometimes hard to comprehend waves you can't see. But sound adds a new layer of understanding when combining it with a visualization.
I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.